is we're going to have a circuit. I got one load, I got two loads, and then I got this third load, and it's got a circle around it. Notice, what I want you guys to do is kind of have a plan in terms of what we're going to do. Now what's going to happen is I'm going to have there you go. So what happened? These three became that, these three became that. I have my RT. So at this point, we kind of got an idea how we're going to deconstruct it. All right? So now we can go about putting in the values. Okay, this one here is going to be 12 ohms. This one here is 10 ohms. But this thing here is a resistor equivalent, and it's going to be what? It's going to be what? 15 ohms. I got 15 ohms in parallel with 10, in parallel with 12. What's this one going to be? I'm sorry, what?
What'd you point at?
These three became this, didn't they? Because their relationship to each other is one thing. They're parallel. Okay? These things' relationship to each other was one thing. They were in series. So these three that are parallel become this, and what do we get?
37.
Has to be less than 10 ohms, right? 12 1 over x, 10 1 over x, 15 1 over x equals 1 over x. Survey says
4
ohms. Okay?
Wait, how did you get that?
What is the Zach, what's the relationship of these three loads? They are in what? What do we know about resistance in a parallel circuit? It's always less than the smallest resistor. And oh, by the way, there's the formula we use to solve it. The reciprocal of the sum of reciprocals. So I go 12, 1 over x, plus 10, 1 over x, plus 15, 1 over x equals, figure out what the sum of my reciprocal values is, then I do what? I hit 1 over x one more time, and that's my total resistance. Remember the formula? Resistance total in a parallel circuit is the reciprocal of 1 over R1 plus 1 over R2 plus 1 over R3. So, sorry? So R1 was 12 ohms, so 12, 1 over x, plus 10, 1 over x, plus 15, 1 over x, equals, so I know what the sum is, and then I hit my 1 over x key one more time.
I see.
Yeah, I got that.
Okay? Now, like I said, avoid the temptation to just kind of jump into the middle of the circuit at this point. Okay? But what I do know is, I do know that I have 24 volts. I do know that I've got 4 ohms, so I have how many amps?
6 amps.
6 amps, good. So this T here was that T. So we had 24, 6, 4 ohms. All right. Now this was a resistor equivalent for what? For 3 resistors that were in, for what preceded it, for 3 resistors that are in
Series. Wait, what?
this was a resistor equivalent for 3 resistors that are in
Oh, never mind, sorry.
parallel. So what value is going to come from here and be applicable here? What's constant in the parallel circuit?
amps.
Amps?
What's constant in the parallel circuit?
Voltage.
Okay, remember, this is a resistor equivalent for these 3 that are in parallel. We'll deal with this one later. But this, so now I'm going to set up a T here, and a T here, and a T here. I got 15, 10, 12. The voltage here, 24 volts. 24 volts, 24 volts. 24 divided by 12, 2 amps there. 24 divided by 10, 2.4 amps there. 24 divided by 15, 1.6 amps there. Now, wait a minute.
There's more.
2 of these resistors didn't have circles around them, meaning what? They weren't resistor equivalents, because guess what? There's the 12, there's the 10. So now I can sit there and take 24 volts here, 24 volts here. Doesn't it make sense that the potential here and the potential here are going to be the same?
Yeah.
Okay. So I've got my 10 ohms, so I've got my 2.4 amps there. I've got my 12 ohms, so I've got 2 amps there. Cool. Now we look at this resistor. This was a resistor equivalent for what?
Series.
3 resistors that are in?
Series.
What's constant in the series circuit?
Amps.
So what value, how much amperage am I gonna have flowing through each of those, and where the hell is it gonna come from? 1.6. My bad penmanship, all right? So I'm gonna have 1.6 here, 1.6 here, 1.6 here. I got 7, 5, 3. So that gives me 3 times 1.6, that's 4.8 volts. 1.6 times 5, 8 volts. 1.6 times 7, 11.2. Now what do we know about voltage drops in a series circuit? Kirchhoff's law. They have to equal the applied voltage. Does this plus this plus this equal the 24 volt for the resistor equivalent? Yes. But doesn't it also make sense that if I got 24 volts here, I'm going to have 24 volts here?
Yeah.
Okay. Guess what? At this point, we solved the circuit. At this point, I mean, I can look at my meters and I can kind of get a pretty good idea of what's going on. Okay? If I look at RT, we said was 4 ohms. IT, 6 amps. How much current is flowing through A1?
6 amps.
All of it, right? Current's flowing through the whole circuit back, so that's 6 amps. What's A2 reading?
4 amps.
4 amps. It's reading the 2.4 that's going through there and the 1.6 that flowed through there, so that's 4 amps. Or, as we said, it's reading all the amperage minus the 2 that went up there. A3.
4 amps. No,
Oh.
2 amps.
Where is it? It's right next to R2. We said 2.4 amps is flowing through there.
Yeah.
Okay? A4? 1.6 amps. Well, which 1.6 amps is it? Is it that one, or that one? It doesn't matter. It's the same damn amperage. Why? Because they're in
Series.
excellent. All right. What's B1 reading? 11.2 volts. The difference of potential across that load. If B2 was here to here, what would it read? That plus that, 19.2, right? If it's here, what's it reading? Well, that plus that plus that, which is also equal to 24 volts, which is my difference of potential across those loads. Okay? The next one's a little bit more pain in the ass.
Listen, what if it were like this?
I'm sorry?
So what if it were like this? I can't really explain it, but what if it instead of 4.5
It is, it's the same. Yeah, it's the difference of potential. The fact that it's up this leg, current flows up through that leg, but the potential is available at that leg. Current, voltage is the potential difference between any 2 points. Current, it matters because current flows.
this will still be.
Ryan, we good?
Yeah.